Hello. So, let's get on to the solar system. Whenever this loads, we can learn. Okay, so we're on the solar system. This should be a little bit of review, but even if you don't know it, pay attention and learn some fun stuff. Okay, so we got some old school ideas about the solar system. We have some new school ideas about the solar system. One of the older models was it's called geocentric, and that's essentially people thought that the Earth was the center of the universe, and that the sun and the moon and all the planets and the stars revolved around the Earth. Ptolemy, or Ptolemy, some people call him. He was the one who generated that idea, and although he was forward thinking for thinking about the solar system, he was completely wrong. Our Earth does not, or our Earth revolves around the sun, and that's the heliocentric model. That was later described by Copernicus, and Galileo refined that model later. And then another guy to remember is Kepler, who really made the modern day model of our solar system that we use today. So, early model was Earth-centered. It's called geocentric. Geo is Earth, centric, center. That was Ptolemy. And then the one we use now is the heliocentric model, helio sun, centric, center. And we know through evidence that that is the correct model. So, here we go. Kepler was the man who introduced the idea of circular or elliptical orbits. So, all of the planets in our solar system orbit the sun, and that's due to gravity. And we'll talk about it a little bit later, how you remember how nebulas form stars. So, essentially, what happened was our sun formed from a gas nebula, and then the excess parts became planets and started revolving around this very hot, very dense center of our solar system. So what's important to know about our orbits is they're not completely circular. It looks nice and pretty with these lines, but it's more of an ovular shape. It's like an ellipses is what we call it. So it's it's an elliptical orbit is what we call it. So it kind of changes a little bit. It's not completely perfect. So, how our solar system was formed. We remember from earlier how stars are formed with a nebula. So, the nebular theory is the theory that most people consider as the best one for our solar system. So, essentially, we had some sort of event with a nebula. Inside of that nebula, a lot of dense particles started getting their own gravitation and rotating around each other, hitting each other, creating energy and more more density towards the middle. And so then once that happened, then that density in the middle started getting its own gravitational pull. And so that's where we get this circular elliptical effect for matter around it. And here we see in 4, the sun is pretty much formed here. The planets are still trying to figure out their own path. It's basically a bunch of space junk spinning around, hitting each other until finally we get our method or our model of the solar system here, which is heliocentric, the sun in the middle, and then the planets gravitating and rotating around the sun. So that's the nebular theory. So the planets here, this is just going to be a quick overview of the planets. So we start with one, with Mercury. It's the closest one to the sun. It's very hot. It's relatively dense. It's basically just a big ball of rock. And then we go to Venus. Venus has a very, very dense atmosphere. So that greenhouse effect that we talked about on Earth, that is exponentially more powerful on Venus. So it's a very, very hot planet because of the greenhouse effect. Then we get to our home, Earth. It also has an atmosphere with a greenhouse effect, but it's much less powerful than Venus. And then after that, we have Mars, which is its atmosphere is pretty much gone. It still has like a very, very thin one, but it's basically just a dead rock. And then between Mars and Jupiter, we have our asteroid belt. So right in this area, we've got an asteroid belt. And essentially that's just a bunch of space rocks floating around in this area, and it follows the elliptical orbit as well. Inside of there, we have some dwarf planets, but they aren't considered planets because of a multitude of reasons. They don't have their own gravitational pull, they're not completely circular, those types of things. Then after that asteroid belt, we have our biggest planet, that's Jupiter right here. It has a small ring around it that you can't see. This dot right here is a big storm that is constantly raging on Jupiter. So, it's just fun information if you want to look it up. It's interesting to learn about. And then we have Saturn, the big, pretty ring one. That's our second biggest planet. And after that is Uranus, and it's got a vertical ring, actually. It kind of looks like it's tilted sideways. And after Uranus, we have Neptune, which now is technically our farthest planet away because we kicked out Pluto, poor Pluto. Apparently Pluto and Neptune change orbits sometimes. So we're talking, hundreds of thousands of years. Every once in a while, these two planets will change their orbit. One will get closer, one will get farther. But Pluto isn't a planet anymore. We kicked it out, unfortunately. So, other objects in the solar system, we have comets, which is basically, when you think about a comet, you think about Halley's Comet. That's like the 80-year comet. Most of you will have been able to see that twice in your lifetime. Comets are essentially just big balls of ice and rock orbiting the sun. Halley's Comet, how my colleague Alex presented it, kind of gets slingshot around the sun. So when it comes towards the sun, it's going faster and faster and faster, and it hits that gravitational pull, and then it gets slingshot out through into the atmosphere, and it slows down out in the outer reaches of the solar system. Excuse me, not the atmosphere, the solar system. So Halley's Comet is just a good example of a comet, and it's got that slingshot effect. Then we've got asteroids. We talked about the belt between Mars and Jupiter. There's also the Kuiper belt outside of Pluto. You don't really need to worry about that one too much. It's basically so far away that it can't affect anything in your life ever. But it's cool to know. So Kuiper belt, something if you're interested, look it up. And then here we have three different distinguishing factors for meteoroids that is very important to know. So when we've got the meteoroid, it's just the object itself floating through space. It's just like a big ball of rock and metal, most likely, to be able to survive all the different weathering factors in space. So we've got a meteoroid, and that's just the object. When that object goes into the atmosphere of the Earth, we get a flash of light and a lot of heat. So we call that a meteor. So the meteor is when a meteoroid gets into the atmosphere of the Earth or of another planet, say Venus, and it creates a flash of light and intense heat. So normally when those meteors occur, they burn up very, very quickly. So when you see a shooting star, that's kind of the thing that you're looking at. Sometimes when we see videos online of just this crazy gaseous ball of fire coming from space, basically, and no one can tell what's going on, that's a meteor. Those are relatively harmless unless they're so big that they can hit the Earth. So when they hit the Earth, we call that a meteorite. And a meteorite is essentially just a meteor that didn't burn up all the way when it entered our atmosphere. So it was able to hit the Earth. And that is very, very unlikely. So the reason why we don't have too many meteorites hitting us is because of our atmosphere, and that whole idea of when a meteor comes into our atmosphere, it burns up very quickly. So I wouldn't be super worried about that, but that's always a danger that comes with living in a volatile space. So then dwarf planets, we've got Pluto and Eris, and then we've got some other dwarf planets inside of our asteroid belt between Mars and Jupiter. But essentially, they're dwarf planets because they're very large. They might follow an elliptical pattern around the sun, but they don't really have their own gravitational pull. They aren't completely circular. They don't hit a certain size regulation. So there are a very there's a multitude of reasons why they're classified as dwarf planets, and I will let the scientists keep their classifications because they know more than I do. But that's all you need to know about the solar system this far. If you have any more questions, you can ask me, or Google has tons and tons and tons of information about the solar system. If you're just looking to get a little more information about that, go ahead and do some research on your own. Alrighty, and that will do it. Feel free, as always, to contact me if you have any questions at all, and I'll see you on the next one.